All right, let's jump straight into this explainer. Today, we're looking at a serious breakthrough in computer graphics, a paper titled A Consistent Segmentation Approach to Image-Based Rendering. This was a massive collaboration between the University of Washington, Adobe Systems, and Microsoft Research. And what they're tackling here honestly sounds like pure science fiction. They figured out a way to generate fully explorable 3D environments from completely flat, everyday photographs. So if you've ever looked at an old photo and just wanted to literally step inside of it, well, this is the exact math and computer science that makes it a reality.
To really wrap our heads around this, we have to start with the big question. How in the world do you turn a handful of shaky handheld snapshots into a fully 3D explorable world? I mean, shooting a panorama is one thing, right? But it is an entirely different beast to ask an algorithm to take unstructured 2D pictures and somehow synthesize a smooth 3D space where you can actually move your virtual camera around. How does the computer know what's hiding behind an object in a flat photo? Well, let's find out.
The secret sauce here is a concept called image-based rendering, or IBR. At its core, IBR is the process of rendering novel viewpoints of a scene just by resampling a set of captured input photographs. So instead of having a 3D artist sit there and manually model a virtual environment, polygon by painstaking polygon, the system actually creates a geometric proxy. Basically, it builds this rough, invisible 3D scaffold based on the depths it mathematically extracts from your original 2D images. Then, it uses that data to project the original pixels into a completely brand new 3D view.
To understand how it does this, we're going to treat this algorithm like a factory tour. First up, making 3D from 2D. Next, finding the camera's position. Third, slicing those images into segments. Fourth, calculating the depths. And finally, rendering the novel view.
Okay, step 1, making 3D from 2D. Now, what's genuinely mind-blowing about this specific research is the actual input it uses. We're not talking about million-dollar Hollywood camera rigs meticulously calibrated on a track. No way. The input here is just a small collection of unstructured, handheld snapshots. Literally the exact kind of stuff sitting on your camera roll right now. The system works totally overtime to synthesize accurate depth from just a handful of these regular, uncalibrated photos. That makes the tech incredibly accessible, but it also means the algorithm has to be insanely smart to fill in the missing gaps.
Moving down the line, we hit step 2, finding the camera's position.
Before it can build a world, the algorithm kind of has to act like a detective. Step 1 of this high-level pipeline is recovering the viewpoints, using a technique called structure from motion. Imagine you're looking at 2 photos of a statue, just taken from slightly different angles. By matching the shared features between those 2 images, the algorithm iteratively estimates the exact projection matrix, meaning the precise position and angle of each camera when the photo was taken. From there, it computes multi-view stereo to grab the depth, and finally renders out those novel views.
But to juggle all those recovered camera positions without losing its mind, the system builds what's called a view mesh. It takes all those estimated camera viewpoints, projects them onto a flat plane in 3D space, and connects them using a Delaunay triangulation. You can think of it like playing connect the dots to create a literal web of cameras. By connecting these points, the system inherently understands which viewpoints are neighbors. And that is absolutely crucial later on when it needs to compare images from adjacent angles to figure out exactly how deep the scene goes. All right, step 3, slicing images into segments. This is where we get to the core innovation of the paper. Before we can accurately nail down the depth, we have to break the image into manageable chunks, or segments. The system initializes this by subdividing the image based on color variation using a quad tree structure. Basically, if a block of pixels has way too many different colors, specifically a color standard deviation threshold above 90, it gets sliced into 4 smaller blocks. But it stops slicing at 8 by 8 pixels. It has a hard limit. This prevents over-segmentation, making sure the pieces are just large enough to analyze without the system getting completely lost in the noise of single pixels. This approach brilliantly advances older optical flow models by adding 4 multi-view stereo extensions. First up, it enforces a soft epipolar constraint. That's a fancy way of saying, if you know where a camera was, you can draw a line of sight to restrict where a pixel should end up in the next photo. Second, it incorporates the sparse 3D point cloud we made earlier as a sort of cheat sheet for where things are.
Third, instead of just checking one neighbor, it consistently segments using n neighboring views. And finally, it merges all those tiny viewpoint differences into one final, highly accurate set of depths. And just to optimize all these crazy segment mappings, the algorithm performs 20 grueling mathematical iterations across all the images. It constantly goes back and forth, updating the segmentation boundaries, double-checking them against neighboring views, and recalculating the depth disparities. It's this massive, intense loop that slowly dials in a hyper-accurate 3D understanding of the scene's geometry. Which brings us to step 4, calculating the depth. After slicing the image 20 times, how does it actually lock in the final depth of a segment? It uses depth merging. Think of it like this. For a single segment, the system draws a 3D ray from the camera's optical center straight through that segment on the image plane. And it does this for all the neighboring views that can see that exact same segment. The final depth is calculated by finding the point in space that minimizes the Euclidean distance to all those intersecting 3D rays. It essentially uses weeded these squares to combine these estimates, throwing out bad data where a segment might be partially blocked. It's a mathematical net that perfectly catches the 3D location of that piece of the photo. But, multi-view stereo isn't always perfectly flawless. Sometimes, especially around the edges of objects, the math gets a little confused. So, the researchers included a really smart, interactive correction feature. This lets a user manually fix errant segments that sort of coast or float weirdly across the virtual field of view. You just click in the interactive viewer, and you can guide the algorithm to fix those rogue boundary segments. It goes to show that sometimes you just need a little bit of human intuition to completely perfect the math. And finally, step 5, rendering the novel view. Let's see how this math actually gets drawn to the screen. To figure out the exact color of a pixel in our brand new virtual view, the algorithm shoots a ray through the virtual image plane until it hits that view mesh we talked about earlier. It figures out which triangle of 3 real-world viewpoints it's looking through. Then it uses barycentric coordinates. Basically, it assigns blending weights. If your virtual camera is standing a lot closer to camera A than it is to camera B, the final image is going to pull much more of its color data directly from camera A. Now, as you move your virtual camera around, segments from different photos are going to overlap. If the system just aggressively rendered whatever was closest, you'd get this really jarring, glitchy flickering called visual popping. But the soft Z-buffer is the absolute hero here. It consistently resolves conflicting depth information by smoothly blending segments based on their distance. Instead of just snapping out of existence, segments smoothly fade out as they get pushed back, keeping the whole experience buttery smooth. For the actual rendering, the researchers built 2 distinct paths. First, you have the real-time GPU renderer. This is all about interactive exploration and evaluating camera paths on the fly at a super smooth 30 frames per second. On the flip side, you have the offline renderer. This one trades speed for the absolute highest visual quality possible, taking its time to generate the pristine final animation. It's really just about picking the right tool for the job. To actually hit that 30 frames per second in real time, the GPU version pulls off some incredibly clever tricks. Step 1. It renders the extended view mesh to an off-screen buffer. Step 2. It renders those sorted segments to 3 RGBA texture buffers. Step 3. It applies our hero, the soft Z buffer, to seamlessly combine the colors. And step 4. It actually uses a reverse soft Z buffer trick to fill in any microscopic holes caused by the virtual camera seeing parts of the background that were totally blocked in the original photos. It's a brilliant way to drastically cut down rendering time. And that pretty much wraps up this explainer, but it leaves us with a truly exciting question to think about. If complex algorithms like this can synthesize entire explorable 3D worlds from just a few shaky, uncalibrated snapshots, how is this technology going to revolutionize the way we preserve our personal memories in the future? Just imagine not only looking at a flat photo from your childhood, but being able to actually step inside it, walk around, and explore that exact moment in 3D space. The math we just looked at is quite literally the foundation for that future. Thanks so much for joining me on this deep dive, and keep learning.